So we're going to talk about hypothesis testing, correlations, and inferential statistics. So we've already been discussing kind of the background behind variables, how we define variables, and I've kind of talked about the fact that knowing what the variable is tells us what kind of statistical techniques we can use. We've also covered descriptive statistics and how we actually can use those statistics to kind of summarize data. When we're talking about inferential statistics, it's a whole category of different types of statistics, kind of like descriptive statistics is a whole category. But with inferential statistics, we're inferring that what we find in a sample population, the people that we actually study, can infer to a larger population. Now, how we do that is more of theory and methodology, but it's important to recognize that when we're talking about statistical techniques that test hypotheses, that look for relationships, that give us statistical significance, that statistical significance is a marker of how confident we are that the results could be found again, and that those results being found again could also give us information about a larger group of people. So you'll often hear the reference to correlation does not equal causation. No statistic gives us causation. There are certain statistics that are more likely to be used in causal studies. However, causation, the ability to say that something causes something else, is a methodological theoretical concept. And it basically revolves around the ability to show temporal precedence, that their cause preceded the effect, that there is no other possible explanation for the results that you found, and you found those results. You found a relationship between two variables. One of them definitely came before the other. It is a causal agent, and there is no other reason you would find a change. That's what leads to causation. Correlations are used throughout government studies. They're done in media. You see correlations all the time. Just recognize that a lot of times correlations are being presented as causal. The media loves to do this. The media loves to find a study that finds a relationship between two variables, and they'll go ahead and make the inference that that relationship is causal. It's one of the reasons we often say correlations do not equal causation, because we're fighting back against that concept. That we want to make sure that everyone that has a well-rounded education recognizes that the statistic correlation simply means there's a relationship. Very few studies truly get to causation, proof that something causes something else. So again, in the language of statistics, there's causal studies and correlational studies. Causal studies are explanation. They're not only explaining how predicting behavior, they're also giving us information on how we could affect behavior. One of the things that almost always makes a causal study is that the independent variable has been manipulated. There's been an intervention. The researcher is in control of that variable. They're assigning people to conditions. And that assignment happens before the outcome is measured. And then, if that is done properly and methodologically sound, we'll look at the statistical test to find, is there a reliable effect? In other words, do we find statistical significance that we're confident that that effect was not due to chance, but is actually due to an actual impact the IV had on the DV, the predictor had on the outcome. Correlational studies are not a lesser form. It's just we need to be very careful that when we're talking about studies that use correlation, that they're purely predictive. They can still explain something of what's going on, but they don't give us information on how we could actually manipulate things, because they don't tell us about causation. Generally, correlational studies, the independent variable is not manipulated. It's an already existing intervention. It may actually be like, for example, you have two different classes with two different instructors and you're wanting to look at the difference. There's a lot of other things that could be causing differences between those instructors, so you haven't ruled out other possible reasons for a difference. That's why it would not be a causal study. Or it may just be existing measures. You might be measuring depression and anxiety to see if there's a relationship. You can't really state that one comes before the other unless you're manipulating it, which might not ethically be true. There's still a statistical test. In this case, it's not necessarily is there an effect that we can use in the real world, it's simply is there a relationship. A lot of times correlational studies will follow purely descriptive studies, and then causal studies will follow correlational studies. In other words, again, science tends to build on itself. Initial bricks of discovery will most likely be theoretical. Are these things related? Is there evidence of it? They may actually be more descriptive. We've done studies where we're finding out what depression is and how we measure it, what anxiety is and how we measure it. We might then do correlational studies where we look at the effects of anxiety and depression to find out, is there a relationship? And finally, depending on the ethics of the study, we might actually try to set up a causal study to find out which comes first. Which one actually would we be able, if we reduce depression, do we also reduce anxiety, or vice versa? So when we're looking at a correlation as far as a statistic, we definitely need to recognize that we're looking at a technique that can only be used with two variables, generally a single IV and DV, and that both need to be continuous. The reason for this is that that allows us to look for a linear relationship, which is what the correlation actually does. So if you have a relationship that is not linear, in other words, if you have low values of one variable results in low values in another, medium values in one results in medium values in the other, but high values in one results in lower values. In other words, you kind of have a U-shaped distribution. You could not use a correlation to look for that relationship. Correlations specifically look for linear relationships. And both those variables, therefore, need to be continuous. And generally, we need to look to make sure that they're normally distributed, which we've talked about previously, and we'll talk about a little bit more in this lecture as well. If that's the case, we can either use correlation or the linear regression. And we'll talk about linear regression in another set of lectures. So correlation is a measure of association between the variables. It is looking to see, is there a relationship? Not that one affects the other, but simply, is there a relationship between the two variables? It ranges from 1 to -1. So when we calculate a correlation, the actual test statistic will range from 1 to -1, with 0 being no relationship whatsoever, 1.0 being a positive purposeful correlation where there is no error, and a -1.0 where there's a negative relationship. As one goes up, the other goes down. That's perfect as well. We will almost never see correlations of 1.0 to or -1.0. They'll probably be more in the range of closer to 0, but still statistically significant. So just recognize that when you actually calculate a correlation, if you come up with a number that is greater than 1 or less than -1, you've done something wrong. The actual notation to let you know that you're reading about a correlation, or if you're reporting one that you actually let people, other people know it's a correlation, is that you actually present the test statistic. And the test statistic actually has a long name. It's Pearson's Product Moment Correlation Coefficient. We shorten that to R, and the R is lowercase and italicized. So if you see a lowercase r and then some numbers, you know you're dealing with a correlation. It is independent of scale of measurement. What that means is that it doesn't care what your actual original scales were. So if one scale was 1 to 4 and the other scale was 500 to 1,000, if one scale was 1 to 5 and the other scale was -2 to +2, it really doesn't care what the scales of measurement are as long as they are continuous scales. And remember, continuous data is that third level. The numbers are labeling, they have magnitude, so higher or lower, and they have approximately equal distance. That's one of the assumptions of a correlation, is that you have that kind of measurement. But other than that, it doesn't care what the numbers are. It's always going to average those numbers out to where the actual test statistic ranges from 1.0 to -1.0. Like I said, the sign does not reflect strength. It simply reflects the direction of the relationship. So a correlation of -0.9 is stronger than a correlation of +0.5. The sign simply reflects the direction. If it's a negative sign, that means there's a negative correlation, which means as one variable goes up, the other variable goes down. And if it's positive, it means as one variable goes up, the other one goes up. The value reflects the strength, so not the sign, but the value. The closer it is to 1.0 or -1.0, the stronger it is. The closer it is to 0, the weaker it is. So this is just a couple of quick examples of some correlations, and notice that they're generally the top two, A and B, are linear relationships. One of them is positive. As one variable goes up, the other one goes up as well. And B is negative. As one goes up, the other one goes down. Both of these are fairly strong relationships. Those dots in the scatter plot are very close to each other, and each dot represents one point of data or one participant and their combined scores on the two measures, the x-axis and the y-axis. The scatter plot at C shows no relationship. So basically, we have a flat line. So the more that line is arced, either up or down in the prediction, and we call this line, by the way, the line of best fit. It is the line that best represents the reduction of error in our scatter plot. So we draw a line, and actually we statistically can allow our packages to draw this line that minimizes the amount of error between each and every point and the line. You can often do this just in your head, kind of visually, but statistically, the line of best fit is actually being calculated to be the line that you can draw through your data that minimizes that error. When we look at C, we see most likely a flat line, and in that case, there's really no relationship between the two variables. Knowing what one variable is really doesn't give you information on the other or vice versa. And D is that example that I mentioned earlier, where correlation would not be appropriate for this data. There's definitely a relationship going on, but it's a curvilinear relationship, not a linear relationship. You need a statistical technique that can actually identify what's going on. It's one of the reasons when we run correlations, one of the things we'll often do is we will run a scatter plot to take a quick look so we can visually see, is this looking linear or is there something else going on? Or are we at C where there really is no relationship? So just a little bit of history. The correlation was created by Karl Pearson. He was a British statistician from 1857 to 1936. He had an influence in Einstein. He wrote the book, The Grammar of Science, and that actually influenced Einstein in his research. He was, like many early statisticians who developed these techniques, he was a eugenicist. And that means that he also believed that the measurement of human behavior, of human ability, of human potential could therefore be used to make better humans. So he was an evolutionist, but he also believed in kind of selection on a human scale. He founded Biometrica, which is the preeminent journal of statistical techniques even to this day, and he created linear correlation and regression. Actually, the reality is he stole it. The person that actually created this was Francis Edgeworth, and I'm going to talk briefly about him. But basically, a graduate student doing research noticed that one of Pearson's correlations, his formula, had actually appeared a few years earlier in someone else's paper, which means that the earliest publication we have of Pearson's product moment correlation coefficient is actually after Francis Edgeworth had already been using the technique. Francis Edgeworth was an Irish statistician. He was not a eugenicist. He wasn't really big into the whole British scene of proving that British people were better. So if anything, we almost feel like in modern eyes, he was a better person. He also was friends with many other people that were involved in the early statistics that we're going to talk about in the various classes. So here's the actual Pearson product moment correlation coefficient. And even though we now know that it wasn't actually created by Pearson, he still gets the credit and we still use his name. It's Pearson's product moment correlation coefficient, or often just reduced down to Pearson's coefficient. It looks pretty complex, but basically what's happening here, it's fairly simple. So for example, we're summing, if you look at this, X and Y represent individual scores. So the first thing we're doing on the top of the equation is we're actually summing everybody's score multiplied by itself. So basically, we're adding up all of the scores of every individual, their score on X and their score on Y, their score on the two variables. We're then subtracting the sum of all of the scores on one variable with the sum of all the scores on the other divided by the total number of scores. That gives us the top of the equation. The bottom of the equation is we're squaring every single score on X, divided or minus the square of every score on X divided by the total of N. And then we're multiplying that by the square of Y minus the sum of Y squared, and again, divided by N. And we're taking all of that and creating a square root. So I know I'm going over this fairly quickly. We have some additional resources that'll get you into a little bit of knowledge on this, but it's more important to just understand theoretically what's going on in all statistics. All statistics are trying to mathematically put the effect, in other words, the relationship of the two variables, X times Y, at the top of the equation, and the total variance, regardless of the combination or the connection or the effect, on the bottom. So that generally is what's going to give us that Pearson's R that's going to range from 1 to -1. So in simplistic terms, R is the amount of variance that covaries divided by all variance in the variables of x and y. So basically, we're looking for the effect over the total noise. So a bivariate correlation measures the association between two variables. Again, I have the equation here. R can also be summed up by this equation, and this is basically just summarizing some of what we've already talked about as far as that previous equation. And when we look at Z, Z is every individual score minus the mean divided by the standard deviation. So if we actually calculated the Z scores for everybody's X and the Z scores for everybody's Y, multiplied those together and summed them, divided by the total number, that would also give us R. So it's an easier way to do the math, a different way to do the math. Both of these will work. Both of these will give you the same information. And this is one of the reasons why we have two different equations. And initially, there was some debate on, again, who actually created this technique. But both of these give you the same information. So let's go through a quick example. We're looking here at cumulative GPA and the amount of candy eaten per day. We actually find there is a relationship, -0.10, which means as your GPA goes up, your amount of candy eaten per day goes down. But it's a pretty small relationship. Again, remember, R varies from +1.0 to -1.0. This is -0.1. So that kind of gives you an idea. So we're going to look at that example, and we can scatter plot that. And you'll see that there is a bit of a relationship here. If we actually calculate the line of best fit, it shows a little bit of a negative relationship. As GPA goes up, candy consumption goes down, and vice versa. So that kind of gives us an idea of a weak relationship. So again, each one of these dots represents a single person. So this is a person with a GPA of 2.0 that eats 2 pieces of candy a day. Now let's take a look at cumulative GPA and GRE in graduate students. And here we see an R of 0.51. So this is the relationship between someone's individual GPA and their scores in the GRE. And again, we see a stronger relationship here. As GRE scores go up, this is a positive relationship because there isn't a negative sign. And as they go up, we basically see an increase in GPA as well. And again, one individual point represents one person. This person had a GRE of 500 and a GPA of 4. This person was actually just exactly as we predicted. GPA of 2.5 and a GRE of 500. Now notice I'm occasionally talking about using that line of best fit for prediction. That is not information that we get from the correlation. That is information that we'll get from the regression, which we'll be discussing shortly in another lecture. And finally, let's look at a strong relationship, the running rate of rats to room temperature. So this is from behavioral science, and here we find an R of -0.93, and we can take a look at that. The temperature here is being measured fairly arbitrarily, but it basically represents as the room gets hotter, the rats run less and less in a maze. And again, we see this relationship, and each one of these data points is the rat's score on these two things. So we're basically then finally needing to measure the meaningfulness or the size of the correlation. So that's the proportion of shared variance, and basically R does not actually tell us a percentage, though it feels like a percentage. It goes from 1.0 to -1.0. It actually needs to be squared to give us the coefficient of determination. And coefficient of determination is just a fancy way to say effect size. So if we look at this, we basically have to square R. So R, 0.51, that GPA versus GRE connected, needs to be multiplied by itself, 0.51 times 0.51. That gives us our proportion of shared variance, or our effect size, which is reported as R squared, again, italicized. In this case, it's 0.2025, rounded to approximately 20%. That tells us that graduate GPA is predicted by the GRE about 20%, which means 80% of GPA is other factors. Who you have, your familiarity with the material, how you're feeling, a lot of other things go into it. But GRE does give us some prediction. Recognize that a lot of times when we're looking in the social sciences, if we're explaining 5% or more of variance, we're often pretty happy that we've discovered at least a part of what's going on. I like to again refer to it, and you'll probably hear it in other lectures, as Vegas odds. Vegas odds are basically random or the house's advantage. What we're trying to do is push the favor in our favor against the house. So if we had to just guess at someone's GPA, we'd be explaining 0% of the variance. With GRE score in hand, we can explain about 20% of what's going on. If we want to figure out the proportion of unshared variance, we simply take 1 minus r squared. So in this case, the unexplained variance is 79.75 on either side. So you'll find different guides to judging the meaningfulness of the size of a correlation, but the general guidelines, rules of thumbs, according to a lot of texts, is that an R of 0 to 0.29 is none to weak relationships. So that's explained as about 0 to 8% of a relationship. And notice I mentioned that sometimes in the social sciences, if we explain more than 5% of variance, we're happy. So this is not talking about whether or not the difference is significant. We're talking about how strong is the relationship. So we might find a relationship of 5% that is significant. That's a different marker, and we'll be discussing that later. However, if we go on, if we actually have an R of 0.3 to 0.69, so explaining 9 to 48%, we're talking about a moderate relationship. And if we're explaining more than 48% of the variance, we have a very strong relationship. Now, I've rarely seen in the social sciences R's of 0.4 or R squares of 0.49 to 100%. We're usually in that kind of 5 to 48% range. And if I actually had a study that was explaining 48% of the variance, I would be ecstatic by that finding. But statistics are not just used by social scientists. These are also being used to look for correlations between behavior in animals and also just behavior in a lot of other sciences. And in those sciences, these are kind of the rules of thumb. So hopefully that gives you a kind of a broad concept of correlations. There will be additional slides and lectures talking about how we actually calculate correlations using SPSS. And there's another slide deck that we are going to be going over as far as inferential statistics. And of course, we're going to continue building on this base of knowledge that we're working on.